curves in industrial design, the Casteljau algorithm. Given the ordered set of n plus 1 points C0, C1, Cn, the expression given by the first vertex times the first Bernstein polynomial of degree n plus C1, second vertex times the second Bernstein polynomial of degree n, and so on, is, for each t, a barycentric combination of the given points. This is the expression of a Bezier curve of degree n for a fixed t between 0 and 1. Given t between 0 and 1, how can we calculate a point ct on the curve? The most efficient way is through the Casteljau algorithm. The Casteljau algorithm. The Casteljau algorithm gives a numerically stable way of computing a point ct on a Bezier curve for a given t between 0 and 1. If the curve is of degree n, the Casteljau algorithm has n iterations. The Casteljau algorithm starts with n plus 1 points, and at each iteration the number of points is reduced by 1. At the nth iteration, the only point left is the sought-after point ct, a point on the curve. Here we have a schematic representation of the Casteljau algorithm. For a cubic Bezier curve, the control polygon has 4 points, C0, C1, C2, and C3, and these are the starting points of the Casteljau algorithm. In the first iteration, the number of points is reduced by 1, and we get 3 points, which are represented in color red. In the second iteration, 3 points are reduced by 1, and we get 2 points that are represented in yellow. And in the last iteration, the 2 points are reduced in 1, and we get the last point, which is represented in green. So on the screen we start with the control polygon of the Bezier curve, and we fix a value for t, in this case 0.2. So on the first stage, we get the 3 points of the first stage of the Casteljau algorithm. These points in red. They are obtained as barycentric combination of the points on the line segment they are lying on. So this point here is a barycentric combination of C0, C1, with proportions t, in this case 0.2, 1 minus t, in this case 0.8. This point, it lies on this line segment between C1 and C2 in the same proportions, t and 1 minus t. And this point lies on the line segment between C2 and C3 in the same proportions, t, 1 minus t. The second stage, we get the yellow points on the segments with ends in the red point, in the same proportions as we did before. This point is a proportion t, 0.2, 1 minus t, 0.8. And this point the same, t, 1 minus t. And on the third stage of the Casteljau algorithm, we get the last point and the segment of the yellow, with endpoints the yellow points, with proportion t, 1 minus t. So this green point here, calculated by the Casteljau algorithm, will be a point on the curve. If we change t to say 0.5, the first stage we get the middle points of the segments, in the second stage the middle points of the new segments, and on the third stage the middle point of the last segment. And this point, again, will be a point on the curve. We change t, we do the same thing, the 3 steps of the Casteljau algorithm to get a new point on the curve. All these points will be on the curve. Every point on the curve is calculated in this way. And we get, finally, calculating many of them, the whole curve. So we've seen how geometrically it can be deduced the Casteljau algorithm. And we are going to see now why it is true analytically. So here we have the expression of the Bezier curve of degree 3. And this is the first point of the first iteration of the Casteljau algorithm, the second point and the third point of the first iteration of the Casteljau algorithm. That are obtained, each of them, as a point in the edges of the control polygon with ratio t 1 minus t, each of them in their corresponding edge. So when we substitute these expressions by the points, we get this expression here and this expression here. And now this point is a point on the line segment defined by C01, C11 at ratio t 1 minus t, which is the first point of the second iteration of the Casteljau algorithm. This point here is a point on the line segment between C11 and C21 in the ratio given by t 1 minus t. And this is the second point in the second iteration of the Casteljau algorithm. When we substitute this expression by this point and this expression by this point, we obtain this expression. And now, this point here is a point on the line segment joining C02, C12 at ratio t 1 minus t, which is the last point of the Casteljau algorithm. The last point of the Casteljau algorithm is a point on the curve. So summarizing, the Casteljau algorithm for a cubic Bezier curve for t between 0 and 1. Here we have the control polygon, and here we have the schematic representation of the Casteljau algorithm. The first iteration of the Casteljau algorithm, we get 3 points. These 3 points are obtained in the corresponding edges of the control polygon at ratio t 1 minus t, the ratio given by t. The points in the second iteration of the Casteljau algorithm are on the line segment that join the points of the previous iteration of the Casteljau algorithm at a ratio t 1 minus t. The final point obtained in the Casteljau algorithm is a point in the segment joining the points in the previous iteration of the Casteljau algorithm at ratio t 1 minus t. The point C of the curve is obtained by taking at each stage the points dividing by ratio t over 1 minus t the segments joining the successive points. For a cubic curve, this is done 3 times.